Hi folks, here's some more 5-minute physics, this time on nuclear rates of decay. So what I'm going to be talking about here is the way that a sample of radioactive material decays and how we can model that over time. So I guess the first thing to do here is to define really the decay constant lambda. If we have a particular isotope, a particular atom, lambda is defined as the probability that one atom will decay in 1 second. So if I have, for example, a uranium-235 atom, there is a fairly fixed probability that that atom will decay in the next second. Obviously, we've no idea when the atom will decay. It's a random process, but the probability is fixed. Now, it's worth noting here that for the overwhelming majority of materials, decay constants are small numbers, very small. So think 10 to the minus 11 or something like that. Who knows? Small numbers, though, even for really quite radioactive materials. So now that we know what the decay constant represents, imagine I have a piece of material. These are the radioactive atoms in it, loads of them now. I'm not going to bother counting them. There are n atoms in here. If this piece of radioactive material contains n atoms, then I can say in the next second, lambda n will be the number that I expect to decay. Because remember what lambda represents is the probability that one atom will decay. So if I have n atoms, lambda n atoms decay in the next second. The next thing for us to define then is activity. The activity of a sample, if you like the radioactivity, A, the activity of the sample is the number of decays per second. So at any given time, the activity is equal to lambda n. Lambda n tells me the number of atoms that are going to decay in the next second, and therefore at any given time, the activity of a radioactive sample is equal to lambda n, where n is the number of radioactive atoms. But, and here's the crux really, as atoms decay, n decreases essentially, because these radioactive atoms decay once and have changed to a different element. So, with that in mind, we find that the activity of a sample will change over time because the number of radioactive atoms that are left in that sample decreases, and that's kind of what we're interested in here. If we want to write some sort of equation for that, we can say that the rate of change of the number of atoms in the sample, dm by dt, must be equal in size to the activity, to the number of decays per second. A. And we can say one more thing, that dm by dt is negative. The number of radioactive atoms in the sample is decreasing, so in fact dn by dt is equal to minus a. Therefore we can write dn by dt is equal to minus lambda n. This is a first order differential equation, and it's a relatively straightforward one to solve. If I divide across by 1 over n, and integrate, I have this type of thing. Integrating 1 over n gives me log n, and integrating minus lambda with respect to t gives me minus lambda t, plus c, my constant of integration. This constant of integration is simply a constant, so I can express that as, if I wish to, as the natural log of another constant, and I do wish to. So I'm going to call that log n naught, and in a minute we'll figure out what n naught represents. With that in mind, I can write that right-hand side as log e to the minus lambda t, and since I'm adding the natural log of n naught. According to the rules of logs, I can write that. So I've got ln n equals ln n naught e to the minus lambda t, and therefore n is equal to n naught e to the minus lambda t. If we think about this, if I set t to be equal to 0, then e to the minus lambda t is just equal to 1, and therefore n is equal to n naught. So what does n naught represent? N naught simply represents the number of radioactive atoms in the sample when we started timing. The number that we started with when t was equal to 0. My original number of atoms, if you like. Now if I look at this equation that I've got up here, A equals minus lambda n, that suggests that the original activity of my sample, A naught, would be equal to lambda n naught. And after some time t, the activity of my sample would be equal to lambda n. So therefore, I can substitute in A for n and n naught in this equation because they're both simply multiplied by lambda. So I could cancel the lambdas. I could multiply both sides of that equation by lambda, and write it as the activity after time t is equal to the initial activity e to the minus lambda t. So these are my two rate equations. This one tells me how the activity of a sample changes with time. This one tells me how this top one tells me how the number of radioactive atoms changes with time. The bottom one tells me how the activity of the sample changes with time. And both of these are, since activity is directly proportional to the number of radioactive atoms, they both give me that very distinctive exponential decay graph, which looks literally exactly like that. Whoopsie. Oh no, I've lost all my stuff. There it is. And that's it. I'll do another video clip shortly with how we can use those two rate equations to figure out half-life and that sort of jazz.